Hello everyone, my name is Chaozhen Ning, and I'm a graduate student from Rice University under the supervision of Professor Yin Ning. Today, I'm excited to present our work, DNN Chip Predictor, an analytical performance predictor for DNN accelerators with various data flows and hardware architectures at ICASSP2020. For this presentation, I will first introduce the background and motivation, and then give an overview of our proposed DNN Chip Predictor. After that, the methodology and the evaluation of our proposed analytical model would be described. Finally, a conclusion will be given to summarize our contributions. As we all know, recent performance breakthroughs of deep neural networks, or DNNs, promise numerous DNN applications. However, powerful DNNs often come at a cost of large memory consumption and high computational energy and latency costs, especially when being processed using general hardware like CPUs or GPUs. As DNN accelerators or chips have the potential to bring in orders of magnitude hardware processing efficiency, there has been remarkably growing demand for exploring or designing DNN accelerators for different applications and DNN models. However, designing of DNN accelerators is very challenging because of the large design space consisting of various DNN models and layer structures, different data flows, and different choices of hardware architectures and IP designs. Also, the required cross-disciplinary knowledge together with the time-consuming hardware development process make it often take months to design a DNN accelerator, limiting the fast development of DNN accelerator elevations and thus DNN's more extensive application. As such, analytical models that are able to predict DNN accelerators' hardware performance prior implementation are highly desired because such models can provide fast evaluation at early chip design stage, enable efficient and systematic design exploration and optimization, and lead to hardware-aware efficient DNN models. While there have been some existing work aiming to development such prediction models, they are still limiting in terms of efficacy of wide adoption. Especially, traditional chip prediction is only validated after the time-consuming implementation, while recently developed chip predictors either only support a certain hardware architectures or are not user-friendly. The advantage of our proposed DNN Chip Predictor is that, first, it's analytic and thus fast. Second, it can support both general ASIC and FPGA hardware architectures. And third, it is accurate in predicting hardware performance as validated using different settings, architectures, and DNN models. Next, I will give an overview of our proposed DNN Chip Predictor. As shown in this figure, the DNN Chip Predictor accepts DNN models and hardware parameters, including hardware architectures, DNN to hardware mapping, and technology-based unit cost as input, and output corresponding energy, latency, and throughput prediction by analyzing the resource utilization, data reuse, and communication patterns. Next, I will introduce the high-level intuitive methodology associated with our proposed analytical chip predictors. Without loss of generality, I here take the energy prediction as an example. From a high-level view, the total energy of a DNN accelerator consists of both the computational energy and the data movement energy, as denoted here as ECOMP and EDM, respectively. Both of these two energy costs depends on the adopted DNN models, hardware architecture, DNN to hardware mapping, for example, data flow, and the process technologies. Obtaining the computational energy ECOMP is quite straightforward which, as shown in this equation, is simply equal to the total number of Macs multiplying the unit energy cost of Mac. Similarly, the data movement energy EDM is equal to the multiplication between the total number of different kinds of data movement and the corresponding energy cost. Well, it's easy to obtain the unit energy cost of different data movements. For example, accessing different memory hierarchies, how to obtain the total number of different data movements or memory accesses is not straightforward, for which I will elaborate in the next few slides. As mentioned, the key challenge to predict a DNN accelerator's energy is to obtain the total number of different data movements or memory accesses NDM. Why is it difficult? First, NDM depends on the adopted hardware architectures, which can take numerous forms, such as different size and shapes of MAC arrays, different multipliers and data trees, different hardware IPs for DNN operations, and different memory hierarchies and size. Second, there are numerous choices DNN to hardware mapping or data flows, which will lead to different NDM. For example, given a 3D convolution operation, which can be captured by a 6-loop description, there are many different ways to temporarily and spatially map the operation into a 2D hardware. Each of such a data flow can lead to a different total number of data movement associated with each memory hierarchy. We can say that the two aforementioned challenges listed here contribute to the large design space of DNN accelerators, making the total number of data movements the key to obtain the total energy cost. In the next few minutes, I will use the data flow example here to demonstrate our method to obtain the total number of data movements and thus energy, which is simple and intuitive. Our method consists of 4 simple steps. First, given an accelerator architecture and data flow, it corresponds to a refresh location in the general for-loop description of the DNN model. In step 2, we can calculate the total number of refreshes as the product of all loop bounds above the refresh location. In this example, the total number of refresh is equal to the product of M3, E2, C2, and F1. In step 3, we will calculate the value of such refreshes as the product of all loop bounds below the refresh location. Finally, we found that the total number of data movements is simply equal to the total number of refreshes multiplied by the total value of such refreshes. To summarize, we are the first to find an intuitive and simple method to analytically obtain the total number of data movements and thus the corresponding energy. Given a DNN model, hardware architecture, and data flow is a high-level flow. Once the DNN model, accelerator architecture, and data flow are determined, the refresh locations in the full loop description can be easily determined. Based on the refresh location, the total number of refreshes and the value of such refreshes can be determined based on the loop bounds above and below the location. The product of them is equal to the total number of data movements, which is the most difficult term to determine when predicting a DNN accelerator's total energy. Following a similar process as the one for energy, the prediction for accelerators latency and resource utilizations can also be obtained. For more details, please refer to our paper. Then I will show our evaluation of the proposed DNN Chip Predictor based on different DNN models and hardware platforms. For performance metric, we adopt the prediction error, which captures the difference between our predicted performance and the hardware measured one. Our experiment considers 3 different hardware platforms and DNN models. When our chip predictor evaluated over the chip measured performance of the Aries DNN chip, this figure shows that the prediction error in terms of memory accesses of DRAM and global buffer GB is less than 18%. The prediction error for latency is less than 16%, as shown in this figure. This table shows that the energy prediction error is less than 6%. Also, by comparing with the synthesized performance of the DNN accelerator called 市电脑, our proposed DNN chip predictor achieves less than 10% energy prediction error, validating its consistent effectiveness for different ASIC hardware architecture. Next, I will show that our DNN chip predictor not only performs well for ASIC accelerators, but also for FPGA accelerators. For example, this figure shows that the latency prediction error will be less than 10%, while this next figure shows that the energy prediction error will be less than 8% compared to FPGA measured one. Finally, I would like to make a summary on our paper. We propose a DNN chip predictor, which can efficiently and effectively predict a DNN accelerator's energy, latency, and resource consumption. Given a DNN model, the accelerator's hardware architectures and DNN to hardware mapping data flows. The advantage of our proposed predictor is that it's analytic, fast, and accurate, and for the first time, it supports both ASIC and FPGA DNN accelerators. Therefore, this framework can contribute to fast development of elevations for not only DNN accelerators, but also hardware-aware efficient DNNs. Okay, that's all of the presentation about our proposed DNN chip predictor. Thank you for your attention.